Hello, I'm Dustin. Our project was to research ideas for braking solutions in future electric soil compactors. So, throughout this project, we researched several ideas. Some were more useful than others. One of the first ones was hydraulic braking. This is basically just swapping the current combustion system in which the compactors use already and replacing them with electric motors to drive the hydraulic pumps. This is a simple solution, however, we chose to look into other ideas. Next, we have regenerative braking, which takes the current kinetic energy and stores it or converts it into electricity to feed back into the system. We can see this used in today's electric cars. Now, we also thought of power off braking, so when the machine isn't operating, these brakes will be applied to hold it. This could be useful in situations such as emergency braking or to stop the compactor quickly. Our final choice, which we explored more, was eddy current braking. This happens when magnets cross a conductive material, creating eddy currents that produce an opposing magnetic force to create torque. Now we will have Matt discuss some of our findings.
Moving forward with eddy current braking, our first task was to derive an equation that we could use to determine the viability of the concept. Using the basic mechanical torque equation, coupled with the electromagnetic Lorentz force and magnetic field strength equations, we arrived at a final braking torque equation, showcased at the bottom left. To test this equation, we built a simple tabletop prototype. Using an electric motor to spin an aluminum disc, we tried to slow its movement using homemade and pre-built electromagnets. While the pre-built was much stronger than the homemade, neither had an appreciable effect on the spinning rotor in the model, which didn't align with the torque predicted using our equation. This led us to reconsider the accuracy of our equation. To develop a more accurate model of braking torque, we turned to a research study in which torque had been modeled, this time taking the air gap between the electromagnets and the rotor into account. This difference, combined with our relatively weak electromagnet, was the reason that we did not experience the predicted effect on our tabletop model. Through an updated braking torque model, graphed next to our original equation at the bottom right, it's obvious that the air gap plays a large part in eddy current braking. We can use this finding to more accurately showcase the viability of the concept of Volvo.